everyone for joining us, and let's go ahead and get started. I'll briefly review the agenda for today. I'm going to go over an overview of RFIC verification, and then we're going to focus in on a problem that everyone faces, which is the problem of mismatch. How to simulate mismatch, the good, the bad, and the ugly. Some simplifying assumptions which we can use as the basis for introducing a new technique which we have called fast yield contributor analysis. We'll go through some examples, and then we'll have a review and give you some additional resources so you can get a chance to take this home and work it for yourself. All right, so I'm going to start, again, as I said, with an overview of RFIC verification. And the first question that always comes to mind is, why is performance verification critical for advanced RFICs? And the primary driver here is that most, if not all, of these advanced RFICs are in some type of silicon technology. This is both for the mainstream applications as well as emerging applications, which is a little bit surprising. So all of the normal standards, GSM, WCDMA, emerging ones now, LTE, et cetera, are all using CMOS technology due to the level of integration. But we also see that for these emerging areas like wireless HD and wireless gigabit in the silicon millimeter wave area, these are also using CMOS technologies. And I think as many of you have seen, there's a number of companies pursuing both CMOS PAs and CMOS SOI RF switches. Also, most wireless design starts are now happening in advanced CMOS technology nodes. This graphic is a snapshot from 2007 of wireless design starts, and you can see even 3 years ago, the trend was moving from the 180 to the 130 to the 90 to the 65 nanometer node. In fact, we have customers now that are actually sampling in 28 and 22 nanometer, believe it or not. So what's the problem, with silicon? On the advanced technology nodes especially, there's a higher amount of process variability. You also have larger wafers. They've gone from 8-inch to 12-inch wafers. And these technologies are not necessarily optimized for RF and especially not optimized for millimeter wave. The RFICs that we're talking about are extremely complex and dense, and they have RF mixed signal and digital circuitry that actually interact together. So that's a problem that needs to be addressed, and verification can help there. There's also this increased pressure to get the wireless products out and to get them to yield at volume. Everybody wants to be in that next gadget, whether it's the iPad, the iPhone, excuse me, or the plethora of new wireless connected devices that are out there. So what is RFIC verification? So it's actually simulating the performance of your RF circuit using various sets of device parameters, operational parameters, as well as you may actually be sampling statistical device models in the course of doing your simulations. There are a number of ways that you can do this. Obviously, there's the kind of nominal simulation approach, which you use to verify your nominal spec. Most anticipated operating and process conditions are used there. And people also do worst-case analysis, which is worst-case or corners. They also do things looking at various process parameters and voltage and temperature. And then, of course, there's the Monte Carlo-based approaches for both process and mismatch. And because of the complexity now with the multi-mode, multi-band support in most of these kinds of radios and circuits, there's some operational analysis that also has to take place. So let's look at something in particular. Let's just dive down a little bit deeper into worst-case corners and PVT analysis, and let's just talk about what that is. So when you're doing worst-case and corner analysis and with process voltage and temperature settings, you're really, you're simulating with a parameter set that's based on the assumption that only a few parameters really affect the performance. These are things like oxide thickness, threshold voltage, sheet resistance, electron mobility, or supply voltage, operating temperature, circuit configuration. So, for example, if you have a variable gain amplifier, maybe there's a particular setting that is problematic, for example. And you'll find these corner models and worst-case models in standard PDKs, and they'll be named. And they have names like typical, fast, and slow, and the various configurations of these for different devices. And the example I give here is like for NMOS and PMOS. If you search that library, model library, you would see nomenclature like TT, FF, SS, FS, and SF, which mean typical for NMOS and PMOS, fast, or any combination of that. Why do people use it? Well, you only need a handful of simulations required to cover the parameter space. And historically, it has been the sign-off run set. This is the corner models have been what people have used, specifically in RF where, you have applicable circuit-oriented corners have been defined. That is not what all foundries deliver. And in a lot of cases, customers have to do these themselves. And that's one of the issues, right, the limitation. So you may not have application or circuit worst-case corner models available, all right, based on RF figures of merit. To an RF designer, what does fast or slow mean with respect to RF metrics like noise figure or IP3? It's very hard for a designer to take the concept of a corner, a fast corner or a slow corner, and understand how that's going to impact the kind of performance metric that he's looking at. The other problem is that it really doesn't give you a lot of insight into what is causing a problem. So you run a corner and it doesn't converge or it doesn't work, doesn't meet spec. There's not a lot of insight there, right, that can help you understand exactly what's causing the problem. So that takes care of kind of worst-case corners in PVT. And next I'm going to talk about the Monte Carlo-based approaches. So these are approaches based on random or directed sampling of the statistical device models built from analyzing how the device characteristics vary from die to die, wafer to wafer, and lot to lot. And I've provided a little example here just to give you the feeling, if you've not used this technique before, of exactly kind of what happens. So when you want to run a Monte Carlo analysis, you've got your circuit set up to run, you've got all of your measurements ready, the simulator actually will go and sample over what's called these process parameters that it finds in the actual PDK. Those are then translated through the statistical device models into a model set for a particular run of the simulator. You can combine that particular model set with voltage and temperature, so you can have static variables, and then your simulation runs. From that point, the loop starts over again, and another random sampling or directed sampling of the process parameters is done, translated back through the device models, and another simulation set is produced. You run thousands of these usually, so that you can build statistically significant results. And that allows you to do things like look at histograms. You can also look at correlations between some process parameters or device parameters and what's going on in terms of your performance. I think you might be asking yourself a question here. And so these statistical models can be process-based or mismatch-based. So what does that really mean? So let's talk about Monte Carlo process versus Monte Carlo mismatch. Monte Carlo process models global variation. So these are the large-scale wafer-to-wafer and kind of lot-to-lot variations. So if you apply Monte Carlo process, you're going to be seeing typically large changes of variation on the circuit. With Monte Carlo mismatch, these model local variations. These are the small-scale variations that occur transistor to transistor for transistors that are very close proximity, in terms of the circuit. So it's very functionally interesting to be able to look at, the matching of transistors that you find in the circuit. So these are basically the two different types, and you might ask yourself, of course, why do I use them, or do I use them? And what we find, which is interesting, is that while statistical device models are available from all silicon foundries, there aren't enough design engineers actually running the Monte Carlo process to evaluate the performance variation. And there's a number of reasons for that, and I'm going to walk through them. Long simulation times. The bigger the circuit you have, you might do a functional path like a receiver or a transmitter. You may also have parasitics. So each simulation takes a long time. So if you have to run 1,000 of them, it's prohibitively long in terms of verifying your performance variation before you can tape out. It's also real expensive too, right? So it's very expensive to have all those 1,000 licenses sitting there to be able to run those, the amount of simulation necessary to get statistical significance. And there are also limitations. So you can run these techniques, and we have customers that do this very successfully, and it'll tell you, you've got performance variation that's unacceptable based on the specifications that you have, but you know what? Monte Carlo doesn't tell you what to do about it. It doesn't identify by itself the sources of the things that are driving the variation, the degree that they impact results, or how various blocks actually interact together to impact yield. And that results in over-design or over-optimization or misoptimization. As a result, what most RFIC designers do is to run only worst-case or corners analysis and mismatch. That's the most practical approach and the most timely approach in terms of getting the verification done for modern RFICs. Now, there are ways for us to reduce both the number and the cost of doing Monte Carlo process analysis, but in this webcast, we're going to focus on improving techniques that RF designers actually use, and in this case, it's the Monte Carlo mismatch analysis. So with that kind of overview of RFIC verification, I'd like to turn the webcast over to George Estep.
Thank you, Paul. Again, my name is George Estep. I'm RFIC Design Flow Specialist for Agilent EEsoft. And as Paul has indicated, we're going to be talking about Monte Carlo mismatch analysis. So let's take a step back and let's talk about mismatch and why it's so important. In the early days of silicon technology development, it was realized that it was very difficult from wafer to wafer and from lot to lot to produce transistors that were identically the same as the previous lots or wafers. But at the same time, it was realized that it was very possible to build devices on the same die, which were extremely close in terms of their characteristics to each other. As a result of these two facts, many, if not most, of the circuits that have been developed for silicon IC technology have been based on the concept of matched transistors, either two transistors or a set of transistors matched together. And there have been a lot of benefits to this approach, including the ability to, maybe cancel out some undesirable transistor characteristics, maybe variation with temperature or with process or with bias voltage, at least to a first order, and sometimes you can cancel out even beyond that. It's also been used to kind of allow you to mirror voltage or current elsewhere out in the circuit. It's a very commonly used technique for many types of circuitry. And in the radio world, what we see is that designers will use differential circuits. And the main benefit of differential circuits is that you can kind of have two representations of your waveform, and you can improve your signal and noise characteristics, especially when you've got the decreasing bias voltages that we see today. And there are many, many other applications that I've seen and probably haven't seen for matched transistor sets in silicon design. So now we've got this situation where our designs are dependent on, and they're based on the concept of matching, because we have big variations from wafer to wafer and lot to lot, but we're expecting the transistors to be well matched to provide good performance in the circuits that we're using. But the fact is that no two transistors are exactly the same. Now, if they're really close on the die, they might be extremely similar. As they get farther apart, they're going to be less similar. And to be able to predict what we're going to see when we manufacture these chips is we need to be able to kind of quantify that. As the device geometries decrease, we're also seeing a trend where these mismatches can be a larger percentage of the total variation, the total device parameter that we see in the circuit. So what happens when we have some mismatch in our matched sets in the circuits that we're working with? The obvious one that I think we all see commonly is that the circuit might not be biased where we intended to bias it. So the operating point may be a little different than was intended. Also, differential circuits, they might be intended to produce some DC level at the output. They might produce the wrong DC level, so that the signal levels going into a subsequent stage in the design may be not optimum for giving you perhaps the dynamic range that you need for your design. And when you're working with radio circuits, you may find that in a matched environment, there are spurious signals that are suppressed, but when you have mismatch effects, you're going to generate sometimes signals that wouldn't be there otherwise. For instance, second-order intermodulation products may crop up that were canceled out when you used the nominal case with matched devices. The bottom line is, if you want to find out what your yield is going to be for your design, you need to see how these mismatch effects are going to affect the figures of merit that you care about. So how is it done? As Paul has indicated earlier, the PDKs that you are getting from your foundry for designing your circuits already include mismatch effects in their Monte Carlo models. So that's good. And in fact, the spectra formatted PDKs that Golden Gate uses have these effects built in, and the way it works is every device at a certain level of design hierarchy gets mismatched from the other devices at that level of hierarchy. And so you have this mechanism in your design kit and in your simulators to allow you to do mismatched Monte Carlo simulation. So the question is, what's the problem? Well, it's one thing to have the capability to do it. It's another to actually do it. What you find is that if you're simulating the nominal case or even doing process Monte Carlo analysis, you're working with a set of transistor models that represent your process, and those transistor parameter sets are used globally by the transistors in the design. When you do mismatch analysis, it's fundamentally different, and the result is that each instance of each transistor ends up having a different parameter set than all the other instances. In fact, what you find by the behavior of the tools, if you're doing a fully extracted layout, sometimes the fingers of the individual devices are broken apart, and each finger then gets its own model. That's a topic we can debate for another day, but the issue becomes one of memory and speed, because the memory consumed by these simulations can easily be 10x bigger than the nominal or process Monte Carlo run, and sometimes can increase by a similar factor. The other big issue here is that these mismatch effects are random. So if you want to quantify how much mismatch you have in your design, you can't just run a single simulation and say, I have this much variation in my result. You need to run a Monte Carlo analysis to be able to get hundreds or thousands of results to find out what the distribution of your result is. Put together, what you find is that these two effects multiply by each other. So you have a longer run for each single run, and you might have to do thousands of them. So now you're faced with using compute resources of 1,000x, 10,000x what you would need to do to run a single corner or a single nominal simulation. Well, what do you do? The thing that's commonly done, one thing that's commonly done in simulators is to make a simplifying assumption. Now, I know we all are scared of making assumptions about everything, about anything, but the fact is that we all do it every day already. So RFIC designers are already using a small signal assumption when they do AC analysis, S parameter analysis, small signal noise analysis, which is a combination of a small signal and large signal simulations. That assumption is made for the express purpose of being able to assume linearity in the circuit and to speed simulation so that you can do many things very quickly. Now, we all do it as a day-to-day course of our business, and we know that this assumption carries risks of inaccuracy, and we know how to verify that accuracy. It turns out we can use a similar type of simplifying assumption for doing fast mismatch Monte Carlo simulations, and we're going to call it the small variation assumption. It's not a small signal, but we're going to assume that the variations in the design kit for mismatch are small. And so the goal here of using this assumption is to get some speed up. So we're going to explore how does this assumption allow us to change our simulation time, the amount of compute resources we need, but also importantly, what does it do to the accuracy of the results? So let's discuss exactly what the assumption is. So the simplifying assumption is called the small variation assumption, and that is the small variation assumption is that mismatch variations in your manufacturing process are sufficiently small that there is a linear relationship between all the varying device parameters and the figures of merit which they impact. Now that's an important assumption, and we'll talk exactly about why it's important for this application. But I will say that we've had several of our larger customers go through with this new capability and verify that for mismatched Monte Carlo simulations, this assumption is valid. They've done simulations with regular Monte Carlo and with the small variation assumption version of regular Monte Carlo, and they're getting very good results between the two. I will also add, just by way of saying, is that for process Monte Carlo analysis, where you have large variations between your transistors, this assumption tends to be invalid. In other words, the results are not the same as if you do normal Monte Carlo. That said, there is some value in being able to use that assumption in those cases as well, but that's not the topic for this presentation today. If you want to use the technologies that we're going to talk about in a minute here with process Monte Carlo analysis, contact your Agilent applications engineer. Okay, so how does this simplifying assumption help me? So there's two main benefits of using the small variation assumption. The first one is that in order to get a set of Monte Carlo results, you can do that by simply running a single simulation and then making linear manipulations from the single nominal result to find all of the other results. So for instance, if you need 1,000 runs in your Monte Carlo, you can do one nominal simulation and then you make linear manipulations on that result, and you can find all 1,000 Monte Carlo results, so all 1,000 trials. We like to think of it as a one-run Monte Carlo. It's sort of feels like you're cheating, I guess. Now, the other big benefit of using the small variation assumption is that you can now apply the principle of superposition. By using the assumption that the characteristics between your device parameters and your figures of merit are linear, you can now say, I don't need to turn on all of my variations simultaneously. I can do them one at a time and sum up the result. That's the principle of superposition. That will be the same as if I had turned them all on together. And by doing them one at a time, we can now produce what we call a mismatch contribution table, which is a mapping of your design, all the devices in your design, to the variation in the figure of merit. So you can now quickly look into your design hierarchy and find out what part of my design is going to have the most impact on whatever figure of merit you're measuring. So the benefit, the bottom line for these two benefits is that you're going to have greatly sped up simulations, at least in the case of harmonic balance simulations, and you're going to have additional insight into the mismatch effects of your circuit. So we're going to introduce a new technology called fast yield contributor analysis. And this is important because it implements this small variation assumption that we've been talking about. By taking advantage of fast yield contributor analysis, we can get speedups sometimes as high as 100x over doing a normal harmonic balance simulation. And when you're using them together for doing mismatch Monte Carlo, we have little to no loss in accuracy of the results. Again, as I said earlier, it does work for process Monte Carlo analysis, but in that case, there is some accuracy impact. But that's not a topic for today. And secondly, we can produce this mismatch contribution table. So there's the option to provide, in addition to the normal Monte Carlo results, this additional mapping between your devices and your design and the figures of merit that you care about. So a fast yield contributor analysis is now available in DC analysis, AC analysis, and harmonic balance, or CR analysis. And it is found in the task setting for the form. So if this form doesn't look familiar to you, it's because it's about to be released next month in Golden Gate 4.5. So, but the form has essentially the same function as the previous versions of the form that you're familiar with. But basically, you go into the task, and under Monte Carlo, you have this new FYC option, which I'll introduce in a second. In harmonic balance, you both driven and autonomous, i.e. oscillator circuits, are supported. We currently do not support noise with fast yield contributor analysis, though we'd like to in the future. I don't have a commit date on that yet. So let's talk about the use model for this tool. So as I mentioned, it's found within the Monte Carlo task for DC, AC, and harmonic balance. And you fill out and you set up harmonic balance just the same way as you would normally if you're running a regular Monte Carlo. The only difference is now you check this FYC, fast yield contributor, box at the bottom. If you would also like the mismatch contribution table, you can click this Compute Yield Contribution Table button. Now, there is a slight speed impact by doing that, but you get the addition of having this important mapping between your figures of merit and the contributors. On the results side, what you find is that FYC results are a superset of Monte Carlo results. What I mean by that is if I just click FYC and I don't ask for the yield contribution table, I get exactly the same results that I would get if I ran Monte Carlo not using the small variation assumption. In other words, I would get all the signals available for all of the trials. I could look at waveforms or spectra. I would also get all of the statistical information, mean, standard deviation, scatter plots, for any performances that I've written to calculate figures of merit for my circuit. But if I turn on the Compute Yield Contribution Table to calculate my mismatch contribution table file, then I additionally get this mapping information between my variation in my figures of merit and the circuit devices that impacted it. If I do have that option on, I will get a new type of result, which is the mismatch contribution table tree. It's available in the Agilent QWave tool, and what it does is you have your performance. So in this case, there was a performance written for power gain in dB, and I now have a tree which represents the entire hierarchy of my design. So I can start at the top level. In this case, I'm looking at the output, the power gain at the top level, and I can see that instance I6 and I19 are the major contributors. Now I can go into I19 and I can do the same thing, and I can work my way down through hierarchy, and I can find the exact devices which have the most impact in terms of mismatch impact on my result. It's a very powerful tool to be able to quickly pinpoint Where is this variation coming from? So let's look at a few examples. I have 3 examples that I'm going to show you today. The first one is an LNA. We're going to look at DC simulation, and we're going to look at power supply current for that circuit. I've got a VCO, and we're just going to look at oscillation frequency, and we're going to look at a receiver gain example. So the LNA is a fairly small circuit. There's only 30 active devices, 0.18 microns CMOS, operating at 2.4 gigahertz. And we're just going to look at DC current. So we're going to look at a simple figure of merit. This could be anything, though. If there's a particular device in your design where you care about the GM of that device, you could write a performance to calculate the GM of that device, and then you could get the impact of the mismatch effects on that device, for instance. Well, we're just going to look at power supply current today. And here's a chart where I've done a comparison. I've run normal mismatch Monte Carlo analysis, 1,000 runs, and I've done fast field contributor mismatch Monte Carlo analysis. And for DC analysis, the benefit of this tool is not to give you a speed up, although I do get about a 2x speed up. The benefit is that you're going to get this mismatch contribution table, which you can't get from the normal Monte Carlo simulation. But you'll see when we start talking about harmonic balance that the speed up is much more significant. In this case, memory consumption was about the same for both simulations. The statistical results for the DC current, the power supply current for this circuit, was about the same. You can see the mean and standard deviations are very similar. The minimum and maximum values are also very similar. That's kind of a rough overview, but let me show you a better way to compare these results. What I've done is I've taken those same results and I've made 2 plots to allow me to compare mismatch Monte Carlo normal simulation with mismatch fast yield contributor approach. On the left here, I have 2 scatter plots from the 2 runs. The red dots that you see are from normal mismatch Monte Carlo, and that's the 1,000 runs that we have made. The green dots are the 1,000 runs created using fast mismatch Monte Carlo simulation. And you can see that in large part the green dots sit right on top of the red dots. There is a little bit of variation around the edges. So it's one way that you can see that you're getting a very good agreement between the 2. Another way to look at this same information is to plot the figure of merit from normal Monte Carlo as the x-axis. So I have my supply current is the x-axis from normal Monte Carlo, and my supply current from fast yield contributor mismatch analysis is the y-axis. And each of these dots represents one of the 1,000 runs. And you can see that I have a very good linear agreement from corner to corner on that result. So I have very good, believable results. Now I can have a lot of faith not only in my results, but I can look at my mismatch contribution table and find out what's having the most impact. Now I should say that this is an example circuit using our example PDK, which doesn't have what I would say good models for mismatch. So maybe you don't agree with some of the results here, but the point of this presentation is to show you the operation of the tool. So what we've done here is I've gone to the top level of the design and I've said, what is impacting my power supply current? And this says that instance I0 and I24 have the most impact on my power supply current. Well, I've circled those in orange on the schematic, and it turns out that I0 and I24 are biased for this circuit. That kind of makes sense for looking at power supply currents. So let's go down into I0. We'll push down in this one, and we'll look at the same information. Now, that is indicating that R29 is the significant factor contributing here, and we can go down into the bias circuit and we can investigate why R29 would be the most critical component for mismatch. So let's go on to our next example. We have a VCO-Divider example. It's a VCO divide by 2. It's operating at 5.4 gigahertz, and there's about 60 active devices in this circuit. We're just going to look at oscillation frequency versus mismatch. So now we're seeing that unlike DC, where you didn't really get a big speed up, you're getting somewhat of a significant speed up. The normal mismatch Monte Carlo simulation took 109 seconds for 1,000 runs, but fast yield contributor mismatch analysis only took 12 seconds. It's about an 8.6x improvement. If we turn on the additional step of calculating the mismatch contribution table, the time goes up to about 14 seconds. So still getting a 7.8x speed up even when we're calculating this additional information. Memory consumption is still small at 188 megabytes. And the results are quite similar. You can see here for oscillation frequency, they're quite similar to each other. And we'll look at our comparison charts that we looked at before. So in the scatter plot, you can see mismatch Monte Carlo in the red and mismatch fast yield contributor analysis in the green. There's kind of an offset between the two. So where would that come from? That's kind of a result of the fast yield contributor analysis. I think I told you earlier that to do fast yield contributor analysis, you take the nominal condition and you do a calculation under that condition, and then you do linear manipulations to find all the conditions. Well, the nominal conditions is sort of a fabricated thing because there's no kind of definition of that. So what we do is we sort of take the middle of all the distributions in the kit. And sometimes that can have a slight difference from the exact nominal. But you can see this is really an offset. So in terms of what's contributing to the variation, it's not going to have any impact on that. And you can see, again, in the X versus Y plot, that there's a very good linear relationship between the regular mismatch Monte Carlo results and the fast yield contributor mismatch Monte Carlo results. So again, we can go in, we can look at our schematic at the top level. We're asking about what's having the most impact on our oscillation, and again, it's pointing into the bias. I'm not going to go through down to the bottom level, but you can quickly identify where your mismatch is coming from. So let's look at our last example. This is a receiver. This is more appropriate in terms of device count to what you're going to be working with. This circuit has 1,000 devices in it, and we're going to look at the power gain. Now this has the LNA that we looked at earlier, and it has the divide by 2 quadrature divider that we talked about in the previous example. We have quadrature mixers driving a complex baseband for I and Q. We have DC offset correction, low-pass filter, and 2 VGAs included. So we're going to compare, again, the performance of these two tools. Now we can see the problem, as we stated it early on, especially when you get into harmonic balance, of the simulation time. This simulation, to do 1,000 runs for this receiver, took 14,000 seconds, which is, about 4 hours. That type of simulation time is actually quite short. Each run, I think, is only on the order of a few tens of seconds. Many of our customers' receivers that we have seen, just a single run in the nominal case might take 10 minutes or something like that. So the numbers can get quite large here. But with fast yield contributor analysis, you don't realize that long simulation time. So the longer the sim is in normal Monte Carlo, the bigger the speed up you'll achieve. So here you can see you've got a 34x improvement in sim time. And even if you turn on the mismatch contribution table calculation, you still get a 25x speed up, and you get the additional information. Now, memory consumption did go up, I think about 75% here, but the simulation results, again, are extremely accurate. They're a very good match with what we had in regular Monte Carlo. Let's examine that in more detail. Again, you can see a little bit more distribution between the green and the red dots, green being fast yield contributor and red being normal mismatch Monte Carlo. But there's a very good correlation. You can see that the trends are all the same. And if we do our scatter plot, our XY plot, you can, again, see a good linear relationship between the two results. And since you calculated the mismatch contribution table, you can see that I6 and I19 are your major contributors, and that's pointing us toward the LNA and the baseband block for this receiver. Now, it didn't indicate the Q channel, and the reason is I'm calculating gain on the I channel only. If I had a performance written for the Q channel, I would get a different set of mismatch contributors from this gain calculation. I'm not going to go all the way down to the transistor level, but you get the idea of how you can work your way through and find out what's contributing. So just to wrap up, the fast yield contributor analysis really provides a new tool which enables fast mismatch Monte Carlo simulations of mixed signal and RFIC designs to enable this type of verification, which was quite challenging to do in the past. This tool implements this new concept of a small variation assumption. And that assumption gets you very significant speed improvement, especially in harmonic balance, over traditional Monte Carlo mismatch techniques. But it also is extremely accurate if you're doing mismatch analysis. And finally, you get this additional information about what is impacting my figure of merit for my design that you simply can't get from normal Monte Carlo or even from your measurements. If you'd like more information about fast yield contributor analysis, please contact your ESOF application engineer, or you can contact Paul or me, and we can provide you with the examples that you've seen shown here today. We have them in a workshop database that you're welcome to look at and experience together with Golden Gate. So anyway, I hope this has been helpful, and we'd be happy to answer your questions. I see there's been quite a bit in chat. Thank you.
Thank you, George. In a moment, we'll begin today's QA. Remember to complete the survey that will automatically launch at the end of the webcast. And as I mentioned at the beginning, by submitting this survey, you'll be providing us with valuable information on how we can offer you more and better webcasts in the future. Now on to the question and answer portion of the event. As a reminder, if you have a question, simply type your question in the chat window and select all panelists in the drop-down menu. We'll try to answer everyone's questions live, so I apologize in advance if we don't get to yours. As I mentioned, if we run out of time, we'll respond to the remaining questions via email. Paul will read out the questions.
Great. Thanks, Carmina. Thanks, George. That's a great overview. We do have a number of questions. One question I think I'll take myself was a question about sometimes for the PDKs, especially for maybe older technologies or special technologies, embedded flash and whatnot, that the statistical models aren't available. Yes, this is the requirement for this technique, whether process Monte Carlo or process mismatch, is that you do need to have a statistical model available. The next question, George, I'm going to let you answer this one. This was from one of our attendees wondering if there's a way to actually limit the number of devices with which we can apply mismatch to during a particular simulation or verification run.
That's a good question, and yes, there is. Let me show you. This is actually a feature that's built into the Monte Carlo tool in Golden Gate, and let me pull up the slide that shows that. But what you see is you have this ability to enable mismatch for all devices or only a list. And in fact, this feature was implemented several years ago because of the problem of mismatch. Many times people say, well, I've got this receiver and it has 20,000 transistors in it, and if I turn on mismatch, no longer does this fit on my computer. And so people will sometimes say, I want to run the whole receiver, but I just want to turn on mismatch in one device or in two devices, however many I can fit. So you click List, and then you have the option to select on the schematic the instances that you want to include. And you can click on a whole block and get those. So you can get one or several blocks. You can put a list of blocks that you want and limit that. Hopefully that answers the question. Good question.
Okay, thanks, George. I've got another question which I'll take. One of the attendees wants to know, we're showing the implementation in IC6, which is Cadence's next generation platform, and the question was, is it also available in IC5? And the answer to the question is yes, all what you're seeing is available in both IC6 and IC5. And in IC5, all you need is Golden Gate, and for the analog design environment, L version. For example, if you were going to run Monte Carlo and other things with Spectra RF, you would have to have the more expensive version, which is ADE-XL. But for Golden Gate, all you need is the ADE-L, and all the rest of this optimization, Monte Carlo, fast field contributor is all built into the standard product.
And also, you don't need the statistical model kit. I will say that the reason the slides show IC6 and they also show a pre-release version of the Golden Gate user interface is because I don't want to remake them when when people move to that. So I usually try to work with the latest technology when I make the slides. Good question.
All right, so I'm looking back through the questions again. This is a good question, actually, and this comes up, I think, George, every time we talk to customers about this, is what is the difference in running fast field contributor and running a regular sensitivity analysis?
Okay, yes, that always comes up. Do you want to take that or me, Paul?
No, go ahead.
Okay. The difference is that you've got this issue when you're looking at some important figure of merit for your design. The issue isn't just sensitivity, it's also how much variation you have. So your, let's say you're looking at gain. Your gain could be very sensitive to some process parameter. But if that process parameter doesn't vary very much, it's not a problem for you because high sensitivity alone isn't the issue. The issue is, you know, higher sensitivity and higher amount of variation. So what this brings to the table that sensitivity doesn't give you is it gives you kind of an overall view of your process and how much the variations are that are in there. So you'll see, actually, let me pull up a curve from something that I plotted. Let me find the plot. If you look at the mismatch contribution table, sorry, you're going to see that what we're looking at is the standard deviation of the output. So in this case, when you look at the standard deviation of the output, you're getting both the variation of the signal and the linear relationship between that variation and that figure of merit. We also have this additional parameter called correlation, and that takes into consideration the fact that there may be other parts of the circuit which are designed to cancel that out. For instance, you may have a bias circuitry which has a matched transistor in a different block from a load circuit that is designed to swallow up variation. So you can't just look at, you know, if you're just looking at sensitivities, you can go horribly wrong here. But we've figured out this idea of it's the sensitivity, the amount of variation, and then how does that variation apply to the total amount that you see at the output? Because some of these, you know, may get swallowed up depending on what's going on in the design.
Thanks, George. Yeah, and just a comment there that if you know, to understand the impact that a particular device might have on a figure of merit, it's actually the product, the correlation between that device's output and the figure of merit times the actual standard deviation of the variation that's seen. So that product actually is a good metric, and that I think is what George is plotting there. That's the metric of what the impact is of a particular component on the figure of merit. Okay, let me go back through and see. I think there were a couple other interesting questions here. One question was on the examples you showed, George. Does the fast yield contributor runs you made have the same number of runs as Monte Carlo mismatch? So when you're doing
yes, they do. All of the runs I did that I showed you today, every run was 1,000. I just picked 1,000 out of the air, but every run was for 1,000 runs. I didn't reduce the number of trials. So if you look at the scatter plots, you can see that pretty clearly, that there's the same number of green dots and red dots. Those represent all 1,000 trials. You can see the Monte Carlo trial number from 0 to 1,000. Okay. Yes, every run that I showed today had 1,000.
Thanks, George. A couple other questions. One was, does the figure of merit have to be set before you run FYC? I'll take this one. In fact, these are just normal performance measurements that you want to make. So just in the normal course of looking at your particular design in Golden Gate, you would have set up what we call performances, which are basically measurements at various points in the design, and all of those that you have defined can be included in the analysis. So it's just, you could take a normal state that you've got, which is where you look at the nominal performance metrics for your design, enable the Monte Carlo analysis with fast yield contributor and mismatch, and it'll automatically pick all those up. You don't have to do anything special there.
But you do have to set them ahead of time. So the answer is yes, but you do have to do that up front.
Yeah, if you don't have any performances set, then you don't have any data to look at. That's correct.
It can't calculate that linear relationship that we talked about. If you don't have a performance to calculate to, it won't make those relationships that we've discussed.
The next one was using it for other analyses besides noise, and I guess I want to make clear here that right now we support the carrier or the harmonic balance analysis. Noise is not included yet. That's something that we're working on for a very soon upcoming release. But we also do AC, DC, and oscillator analysis. So that was one of the other questions that came up. Carmina, how much more time do we have for questions?
We have we have some time for a few more questions, Paul.
Okay. George, you see something?
Paul, I have a question here that came to me privately, so maybe you don't see it on your screen.
Okay, good.
It looks like maybe it's already answered. What is the difference between sensitivity analysis and linear Monte Carlo analysis? Yeah, I think we've already answered that. The difference between sensitivity, maybe he asked that to the whole group as well. But the difference is that we provide both the amount of variation as well as the sensitivity in a form it's also in a form that's accessible. It's your real Monte Carlo simulation. So it's a little more valuable in looking at yield than a sensitivity analysis is. I think there's one more like that. Go ahead. Do you see any more, Paul?
Yeah, there's one, and I'm thinking about this one, and maybe maybe George, you have the answer to this. So there's a good question about, once the mismatch table is made, can fast yield contributor reuse the data and do the analysis only for devices which impact more for further runs?
That's a good question. Not yet, but we will certainly request that as an enhancement. That sounds like a very good idea. Thank you.
Okay, Paul, we have time for one more question.
There was one question that came up, and it's another interesting one, was, does the figure of merit have to have a Gaussian distribution? And the answer to that question is, no, it doesn't. It's you could have something you're measuring for a performance that basically lots of different parts of your circuit contribute to that. So you have bias circuits and your LNAs and mixers and other associative things that feed into the overall result. And they feed in different ways. So even, in fact, they all may be producing Gaussian outputs linearly related to the figure of merit. As they combine, when you look at the actual final measurement, they could create skewed distributions. In fact, they could create bimodal distributions. The linearity assumption does not require that those are going to be Gaussian. So we have cases both internally and also with customers where definitely the figure of merit's not Gaussian.
Okay, Paul? Paul, can you hear me?
Yes, I can.
Oh, very good. Okay, Paul, I believe that's all the questions that we have time for today, and I was hoping to get some closing comments from you.
Sure. Yeah, I hope this webcast has helped everyone both understand the need for the various types of verification for RFICs, their respective benefits and limitations as we went through, and also this new technique that we described as fast mismatch analysis, because it can improve the verification time, the cost, and most importantly, things that standard Monte Carlo either process or mismatch can't give you, which is the insight into the circuit blocks and elements that are the sources of the variation, so that you can actually improve the circuits to have less variation, to be more reliable, and therefore yield higher. For all of you now that are interested in looking at this for yourself and to see how this technique can benefit you on your own designs, I encourage you to try it for yourself. If you already have a copy of Golden Gate, you can go ahead and use it immediately. Hopefully you've got at least version 4.4.0 or above. Or contact your local eSoft representative or visit our website, and you can sign up for a demonstration or an evaluation. And finally, I want to thank you all for spending your time with us today, and I recommend that you keep a lookout for additional webcasts and the Innovations in EDA webcast series. Thank you.
Thank you, Paul, and thank you, George. Thanks very much for your presentation. As we wrap up today's presentation, I want you to know we will email you a link when the on-demand version and the PDF slides are posted on our website. Our next Innovations in EDA webcast will be on November 11th, and it's titled Applying the Latest Technologies to Mimic Design. If you're viewing the on-demand version of this webcast and have a question about any of the material, you can email the presenter, Paul Kolstock, and George Estep at Paul_Kolstock at Agilent.com or George_Estep at Agilent.com. I'd also like to remind on-demand viewers to please fill out and submit the webcast survey. I'd like to thank everyone for attending today's event, A Practical Approach to Verifying RFICs with Fast Mismatch Analysis, brought to you by Agilent, eSoft, and Microwave Journal. The copyright of the presentation materials is owned by Agilent Technologies. For a current schedule of the live and on-demand events, please visit us at www.agilent.com/find/events. I'm Carmina. Thank you for joining us, and have a great day.